Okay, good morning, dear students. Uh, Today we will learn about the particular integral for the linear differential equation with constant coefficient. In our previous lecture, we already done about the complementary function of this type differential equation. Now, the process for finding the particular integral is, if we have a differential equation, this is the differential equation, d to the power n y upon dx to the power n, a1 d to the power n minus 1 y upon dx to the power n minus 1, and a and y equal to x, where x is the function of x, and this is the linear differential equation, and all the a1, a2 and an are constant. So this is the linear differential equation with constant coefficient. Now the particular integral of this type differential equation, we can calculate the particular integral of this type differential equation using the rule pi equal to x upon d to the power n a1 d to the power n minus 1 and so on. Or we can, because we can write this equation in the form of this d to the power n plus a1 d to the power n minus 1 and plus dot dot so on, and a and y equal to x. Now, according to the behavior of this function, we have many cases for calculating the particular integral. Behavior means, suppose fx equal to e to the power ax, then fd, then the particular integral equal to e to the power ax upon fd, where fd equal to this denominator part. We can denote this denominator part by the symbol fd, because this is the function of d, and we already know about the value of d equal to d over dx, right? If x equal to e to the power ax, then the particular integral is e to the power ax upon fd, and we can easily calculate the particular integral by replacing the value of d with a. Okay, if we put at the place of d equal to a, then this is the answer of the particular integral for this type function. But always fa not equal to 0. Denominator part, if denominator part equal to 0, then this function does not exist, because something upon 0 equal to infinite. So always fa not equal to 0. Case second, if fa equal to 0, suppose that in any case when we put a at the place of d and the denominator part convert to 0, then the further process is, if fa equal to 0, then fa upon fd, then the particular integral of fa upon fd equal to x f e to the power ax upon f dash a. Similarly, here is f dash a is not equal to 0, but if again f dash a equal to 0, then the particular integral is x square e to the power ax upon f double dash a equal to f double dash a, where f dash a is the one-time differentiation of the denominator part with respect to d, f double dash a is a two-time differentiation of the denominator part with respect to d, and so on. Again, if f double dash a equal to 0, then in next term we can calculate this particular integral like this, x cube e to the power ax upon f triple dash a, and similar, and so on. Let us take an example of case first. This is the question: d square plus 5d plus 6y equal to e to the power x. In this question, if we want to calculate the particular integral, because we already know about the complementary function, the complementary function of this question is, first we need to calculate the roots of the auxiliary equation. The auxiliary equation is m square plus 5m plus 6. Sorry. Now the roots are, the factors are 3 plus 2 m plus 6, and the factors are m square plus 3m plus 2m plus 6 equal to 0. Now the factors are m plus 3 and m plus 2 equal to 0. So we have the roots are minus 3 and minus 2. So the complementary functions is c1 e to the power minus 3x plus c2 e to the power minus 2x. In this lecture, our target to learn the particular integral. So the particular integral of this part is pi equal to e to the power x upon d square plus 5d plus 6. Now, the case first is if x equal to e to the power ax, we have the e to the power x. So what is the value of a? The value of a is 1. The value of a is 1. Now the first we put the value of a in denominator part, and when you put the value of a in denominator part, then e to the power x, and this is the 1 plus 5 into 1 equal to 5 and 6 e to the power x upon 12. So denominator part not equal to 0. It means the particular integral of this is e to the power x upon 12. And in the second example, the pi equal to particular integral equal to e to the power minus 2x upon d plus 2 and d minus 1 to the power 2. Now, if we want to put the value of a in denominator part, the value of a equal to minus 2. When you put minus 2 here, then denominator part convert to 0. But we have two two function in different bracket in the denominator part. One is this and other is this. So first we solve this part, okay, and then it is equal to 1 upon d plus 2, and the particular integral for this part is when you put minus 2 here, then this part not equal to 0. So the particular integral is e to the power minus 2x, and this is minus 2 minus 1 to the power 2. Now this is convert to 1 upon d plus 2 e to the power minus 2x upon minus 3 to the power 2 equal to 9. Now the second part is 1 upon 9 e to the power minus 2x upon d plus 2. Okay. Now when you put minus 2 here, then denominator convert to 0. So the further process for calculating the particular integral is, now we can use this process case second. First we differentiate the denominator part, and then we put the value of a at the place of d. So the differentiation of denominator part is d plus 2, and differentiation of this with respect to d is 1 plus 0. So differentiation of denominator part is 1. Now it is equal to 1 upon 9 e to the power minus 2x upon 1 upon 9 x into x, because this is x into e to the power ax upon f dash a, x into e to the power minus 2x upon 1. Okay. Now in denominator part we have no any d, so the answer of this so the particular integral of this question is x e to the power minus 2x. Okay, students, these are the two examples for case number first, second. In our next lecture we will learn the another cases for calculating the particular integral, and we will solve the example with respect to the another cases. Thank you.